Hello everyone. In last section, we discussed the 4 voting methods and studied how to apply them to determine the winner of an election. In this section, we are going to discuss the defects of each of the voting methods based on some criteria. Specifically, we're going to see how the border count method fails to satisfy the majority criterion. We are also going to see why the plurality method violates the Condorcet criterion. And we will study why the pairwise comparison method fails to satisfy the independence of irrelevant alternative criterion. And finally, we will study how the plurality with the elimination method fails the monotonicity criterion. First of all, let's see what the majority criterion is. It is defined as if a majority of the voters, which means more than half of the voters, rank a candidate as their first choice or the first preference in the preference table, then that candidate should win the election. It is clear that the plurality method and the pairwise comparison method satisfy the majority criterion. So this example is to illustrate why the border count method violates the majority criterion. Here, we first use the border count method to determine the selection from A, B, C, and D by the given preference table. And we will see if the selection satisfies the majority criterion. And from the preference table, we see the 3 columns of a preference list. This is because we have a 3-person panel, which means there are 3 voters. And here we have A, B, C, D 4 candidates. So based on the border count method, we give the first preference 4 points, the second preference 3 points, the third one 2 points, and the last one 1 point. And the result shows that the border count method suggests D is the winner. But if we apply the majority criterion, we see the selection should be C because C has the most first preference votes. Then we introduce the Condorcet criterion. It is defined as if candidate X can defeat each of the other candidates in a head-to-head vote, then X is the winner of the election. Now, we look at an example showing the plurality method violates the Condorcet criterion. 7 members vote for the selection from countries H, I, and J by the plurality method. From the preference table with only the first preference row, we see that H has the most votes, and it should be the winner. Then we need to complete the preference table so that in head-to-head voting, country I defeats both H and J. Because country H defeats I in the first 3 ballots, country I must defeat H in the remaining 4 ballots. So we fill the 2 boxes below I by H and the remaining 2 H's below the 2 I's. Then we also want country I to defeat country J. But here J has already led I by 2-0. So we should fill the blanks in the last row by J and the remaining boxes by I. So the result should be this way. So this problem shows that even if H wins the election by the plurality method, it does not satisfy the Condorcet criterion. Then we introduce the independence of irrelevant alternative criterion. It is defined as if candidate X wins an election, some non-winners are removed from the ballot, and a recount is done, then X still wins the election. For example, the plurality method could violate this criterion. The Board of Supervisors votes for a method to raise taxes. The candidates are H, A, and G. First, we use the probability method to make the decision by the given preference table. Then, we check if the vote satisfies the independence of irrelevant alternative criterion. From the preference table, it's clear that A should be the winner because it has the most first preference votes. So what we are really asking is whether the removal of one of the losing options changes the outcome of the election. Suppose now we remove H from the preference table. So we have a new preference table containing A and G. Then we find G wins the election because it has the most first preference votes. So the independence of irrelevant alternatives criterion is not satisfied because the removal of H changes the voting results. The next example shows the pairwise comparison method can fail the independence of irrelevant alternatives criterion. A board of 18 members votes for the place to hold a meeting by pairwise comparison method by the given preference table. The candidates are A, B, C, and D. Now the problem is to first determine the winner by the pairwise comparison method and then to identify if the results satisfy the independence of irrelevant alternatives criterion if we remove some losing candidates. Because we already know how to perform the pairwise comparison method, here I just give the results. A should be the winner. If we remove B and C, the preference table only contains A and D, and we see that D defeats A by 10 to 8, which means D is the winner now. So it does not satisfy the criterion. The last criterion is the monotonicity criterion. It is defined as if X wins an election and in a re-election, all voters who change their votes only change their votes to favor X, then X also wins the election. We use an example to explain this and see how the probability with elimination method violates this criterion. The preference table here shows election among C, K, and W. We first apply the probability with elimination method to determine the winner. Then, 3 voters who previously preferred C are going to change to support W. But after some consideration, W asks the 3 voters continue to vote for C instead. It may be a little complicated here, let me explain. As highlighted in the preference table, the 3 voters originally preferred C to W to K. If they change to support W, the preference list will be W to C to K. So we are going to consider why this will cause W trouble instead. First of all, we determine the winner by the probability with elimination method. It gives W to be the winner because we already discussed how to apply the probability with the elimination method. I just give the answer here. Now we change the highlighted column to be W, C, and K. We first remove C because it has fewest first preference votes. Then, in each column, we move the remaining candidates up to fill the blanks. Then we can see the winner is K because it has 17 first preference votes while W has 15 votes. This is why W does not want the 3 voters to change. Based on the discussion above, we reached a conclusion which can be stated as the Arrow's impossibility theorem. It is in any election involving more than 2 candidates, there is no voting method that will satisfy all of the 4 fairness criteria.